Okay, this should be the last one. Fn goes to f pointwise. You've heard this all before. We've done everything so far that we need to do to prove this differentiable, and this is a standard differentiability argument to show that this thing is less than epsilon. That's going to show that f is differentiable and f prime equals g simultaneously. I've shown that this thing is less than or equal to epsilon over 3. I've defined what capital N is over here. I've shown that this thing is strictly less than epsilon over 3. The only two things to show left are the blue thing here. I need to show that this thing is less than epsilon over 3, and I need to define what delta is. And I can do those two things simultaneously right here. Actually, let's do this. I'm going to have a different lemma. Here's a lemma, and this will take care of the blue part here. It's a blue lemma. And what that says is, since all f sub n are differentiable, there exists a delta. Well, actually, I should state the theorem here. Sorry. Again, I started proving it. I should tell you what I'm going to prove. I'm going to prove that f sub n of x minus f sub n of c over x minus c minus fn prime of c is less than epsilon over 3 for all x belonging to the interval a, b, such that x minus c is within delta of each other, where delta is to be named later in the following proof. Well, here's the proof, and then we're done. So, because notice that this is going to give us, once I name the delta here, that's going to give me the delta, so I'm proving both of them simultaneously. I'm showing what the delta is right there, and I'm showing that this thing is going to be less than epsilon over 3, which is the blue part right there. Proof. Here I already started writing this. Since Fn is differentiable for all n belonging to natural numbers, capital N is a constant now. Fn is differentiable. By definition of differentiability, there exists a delta bigger than 0, such that basically exactly what we need. F sub n, this quotient here, which is associated with derivatives, basically Fn is differentiable at c, which is exactly the statement. This thing minus the derivative, since we know it exists, has to be less than epsilon over 3 for all x belonging to here that are in the interval. And that's exactly what we need. Right? So I'm just basically applying the definition of differentiability to get that, and I have it. So and delta is as below right there. So in short, to summarize, in short, it's like the 5th screencast. Fn goes to f pointwise, f prime goes to g, then f is differentiable and f prime goes to g. So I can do that simultaneously by showing this thing is less than epsilon. I use the mean value theorem and the order limit theorem to show that this chunk is less than epsilon over 3 whenever capital N is bigger than or equal to n1. So I haven't nailed down my capital N yet. Then I showed that this thing is less than epsilon over 3 because f prime converges to g uniformly, in fact. I use the uniform continuity or uniform convergence over here. But this thing, I just use pointwise convergence. As long as n is bigger than or equal to some n2 that I got from this lemma, this n2 right here, that should have been purple probably, then I'm okay. So I can fix my n and I get this, and then it's just a matter of showing that this thing is differentiable. Fn is differentiable, so I can make this less than epsilon over 3. So this derivative statement is less than epsilon over 3 plus epsilon over 3 plus epsilon 3 equals epsilon. So f is differentiable because this quotient minus something exists. And then this something happens to be g, so g is equal to f prime. And we are done, finally.